Welcome to Teardown Tuesday, and yes, we're going to tear apart this Atten PPS3205T-3S, lovely name, precision programmable power supply. So no mucking around, you know what we say here on the EEVblog, don't turn it on, take it apart. And here we go. We expect inside this thing a big ass transformer, of course, because this thing's a couple of 100 watts worth, so it's going to dominate the thing. Hopefully we get some metal rods going through so it's all nice and sturdy. I suspect not, though, although it's a hope. For this kind of cost I don't expect real super duper metal chassis and all that sort of stuff, but anyway, it could all be plastic attachments up the front like it was on, say, the Co-Rad supply and others, but we'll see. Now, because this is a precision power supply, 0.05% class instrument, I expect there to be a decent DAC per channel in this thing, and a decent ADC. None of this resistor-based DAC rubbish we saw in the Co-Rad. It should be quite well done. Well, at least reasonable, like using maybe a microchip brand 12-bit DAC or something like that. So that's what I expect to find in this thing. Multi-boards, there'll be multiple boards. There'll be one maybe up the back near the heatsink, of course, for the power supply, for the main power supply. Maybe a shared heatsink between all the channels or something like that. We'll find out. So, but ta-da! Yep, we're out. There we go. And the lid. There we go. We've got no shake-proof washers under there, but at least it's it's reasonably solid. And yeah, we have metal bars going across here, but they go into a plastic surround, plastic front panel here. So yeah, not the sturdiest thing in the world, but really, I was hoping that would get a bit more than just the folded front panel with the plastic, metal bars into the plastic front. But this thing's built down to a price. This is $450 worth of precision power supply. So let's take a look in here. I instantly see some temperature sensors on the heatsink. There we go. Thermal switches, thermal cutout. So there you go. It does have thermal protection on both of these heatsinks. It looks like they are separate. We'll get in there and have a better look, but they do look like as a separate one. I mean, they're very close, so it's going to be a lot of heat shared between those, but they are physically separate. So it looks like, here we go, the third channel. Let me check over here. Yep, there we go. There's our 3 power transistors. Let's call that channel 1 down in there. So channel 1 has its own heatsink with its own thermal cutout. And over here, channel 2, there's the 3 devices as well, 3 power transistors. We'll try and get in, or bridge rectifier and power transistors. But there, looks like they've tacked on the third 5-volt channel. So the third channel here, this, it's only low power. It's only 6 volts at 3 amps, so it's only 18 watts, but it does share the heatsink for, say, channel 2 here. So really, if you're using both of these at the same time, you may not get, if you're loading down channel 3, you may not get full capacity on channel 2 as you would for channel 1 over here. So that's just something to remember. We're going to have a look at the big caps here, but yeah, look at our big, beefy power transformer here. It's absolutely enormous. That's where most of the weight goes in. We'll have a look at the sticker on there, but yeah, we've got one main baseboard down here for all the power supply. Looks like we've got our DAC slash ADC board, one of those for each channel. We've got our serial interface board over here. We'll take a look at all these. There's our relay switching. We've got measurement circuitry on the front. We've got another board, oh yeah, that's probably the channel 3 DAC/ADC board. We've got our display board up there. And let's check out our transformer. It is 240 volt one, because this is an Australian version. It is labelled specifically for this particular model. It would be different for the different models, of course. And it's going to have lots of multiple taps. Look, we've got 0 volts, 7.6 volts, 19 volts and 34 volts, and they would correspond to the taps that we measured in the review of this thing as well. So they're all rated for each tap rated for 5 amps, so it'd select those with the relays. And so that, yeah, it matches the, you know, the 5 amp output capability, I guess. And there's going to have 2 of those, so going to have one for channel 1, one for channel 2. Then they've got an auxiliary tap of plus minus 17.5 volts here, only low power for the control circuitry, 0.35 amps. So there's the second channel. It's exactly the same as that channel there, both 5 amps. And it looks like they've got 2. Yeah, each channel has 2 17.5, 0.35. And then there's another one at 11 volts at 3 amps, and that's for your 5 volt output. And there's another tap, 11.5 volts at 0.8 amps for more miscellaneous circuitry. Woo! Man, what a beast of a transformer. So let's look at the one individual channel we've got here. Here's our 3 input taps. So here's our common, and we would have our 7.6 volts, our 19 volts, and our 34 volt taps. And there's the 2 relays down in there to switch between those various taps. The reason that you have taps like that in one of these linear power supplies is because, well, if you've got one at 34 volts for your maximum output voltage capability, and you've got 5 amps output current, whoa, you're going to be dissipating a huge amount of power in your heatsink. That's why they can get away with making this heatsink so small for like 150 odd watts, you know, per channel on this thing. That's, I mean, you know, this is not a big enough heatsink to dissipate, you know, 150 watts. So they keep the thing low. The way they keep it small is to have the multiple taps, just to ensure, and hopefully, if you designed it right, the worst case dissipation capability in your heatsink will be the lowest, the highest voltage differential across from what tap you're using to your output voltage. So at a certain current, therefore Ohm's law, that power has to be dissipated in the pass transistor down there. And then down in this section we have another small relay, couple of heat sunk little regulators, I'm assuming. There's our other transformer tap coming in there, that plus minus 17 volts for the control circuitry. And then they've got another connector here which goes off to the digital board with all the control circuitry. And then we have this vertical riser board here which presumably has the DAC control on it for setting the output voltage and output current. And if we take a look at the power transistor down in there, bingo, we have a 2SD1047 NPN power transistor specifically designed for these applications. There it is. This is the ST data sheet, but there's many manufacturers of this one, assuming that they're genuine. I'm not sure who the manufacturer. I think it had like a V on it or something like that, but it's specifically designed for linear power supply applications, 140 volt, 12 amp job. And if we have a look at the Sanyo data sheet here, interestingly it says, check it out, on-chip ballast resistance. And well, that's ideally what you want on here when you combine the multiple channels. You don't have to have an external ballast resistance. You can just parallel the transistors, takes care of it for you. Very nice. Apologies for interrupting the teardown, but I'm pissed off. You know why? Because I just spent hours shooting this bloody teardown, and then I just spent hours trying to recover the data from my pain in the ass, piece of shit Canon HF G10 camera. Somehow screwed up all the video files. There were like 80 clips that I shot for this thing, or most of them are completely screwed. There are only a couple that seem to actually recover properly. They wouldn't load into my bloody video editing software. They wouldn't do anything. Wasted freaking hours doing it, and now They're useless. So I've got to reshoot the whole bloody thing. I only started with like the clips you saw before this because I shoot the thing in sequence. So now I've got to reshoot the whole bloody thing, the rest of it, and I'm pissed off. So if I'm a bit terse, or I'm not my usual self, or I miss things, or whatever, from now on for the rest of this review, you'll know why. Breathe in, breathe out. Alright, let's look at the mains wiring, shall we? See if it's nice and safe. Deja vu. Here we go. Yeah, here's the main switch, real clunking main switch on the front. We've got heat shrink tubing here on the actual connections themselves, and we've actually got extra insulated sleeving over the wires because they have to go under the board over here, so that's a nice little touch. They know what they're doing there, and they come up over to the IEC connector at the back. They've got heat shrink under that, not a problem. Don't really like the way they've done the earth. This is fairly typical of these kind of products. They've just got it going down to the lug down on the board here. I don't like the ones that just go to the board, but anyway, it'll do. I'm not happy with all the residue and crap around the board here. That's, you know, it's not good at all. And we'll see that further on the SMD assembled parts. But all this stuff is actually on the side of the connectors here is actually glue to hold the connectors in place to stop them vibrating out. They shouldn't, because they're usually friction, and or these are only friction ones, I think, or they might have a small interlocking tab in there. But anyway, they've gone the extra step to glue them in, so that's actually okay. And the cabling from the power boards at the back through to the front panel binding post board, all 18 AWG cable, so that's not bad at all. So they're all cable tied in place, which is good to see. So we've got here's the 5-volt channel and the second channel going over there down to the main board, and also we've got the there it's tucked under there somewhere. Where's the other board? Where's the other channel? There it is. Yep, it's tucked up under there, comes across here, and there it is, going down to the front panel binding post board, which we'll take a look at. And here's the bimetal thermostat switch, and they're KSD302 type, really, you know, common as mud, and really cheap. Very simple and very reliable. Now, I haven't looked up the data sheet for these, I don't recall, but it's got 80 on there, so I'm going to presume that that's 80 degrees Celsius cutoff for that. And there's one on each heatsink here. They've actually got two heatsinks, which this one over here is shared between channel 2 and channel 3, and this one's just dedicated to channel 1. Now these are actually a 10 amp rated contact in these, so they could actually use these to directly switch the output, but they don't, of course. They've already got relays that do that, and you can tell they don't do it by the little pissant wiring they've got going into these things. And you'll notice that they're actually wired in parallel there. So these are just actually used as switch inputs to the micro. I presume goes into the micro, which then tells it, well, over temperature, shut off the output relays. So by having those in parallel like that, obviously if either one of these heat sinks goes over temperature, it's going to short the contacts and trigger the alarm to shut down. But it doesn't know which one has gone over temperature, either channel 1 or combined channel 2, channel 3. So it's a bit inflexible in that point of view. Like if channel 2, channel 3 overheats, it's going to shut down channel 1 as well, because it doesn't know. It's just going to shut off all the outputs. And here's the channel 3 6-volt channel pass transistor, and it's the same type, 2SD1047. And even though that's a bit overkill for that sort of channel, it makes sense because, well, you've already got 4 of them in your in your design, in your bill of materials. So, well, why not just reuse it for that channel? So instead of saving a few cents, the designers have just gone, oh, bugger it, we'll just reuse the existing transistor. It does the job. It's a no-brainer. It's a no risk. So let's just get on with it. So they've done that, and as you can see, it is got a little sill type pad in there, insulating that from the heatsink, of course, because channel 2 and channel 3, this is the pass transistor for channel 3, they share the same heatsink, but they're completely isolated channels, so you don't want them shorting out. So it's very important that that is well insulated from that heatsink, because you can see the other transistor down there for channel 2, it's not isolated from the heatsink. It's just directly connected, bolted straight on there. So they've done well. They've actually insulated the individual wires there, because they don't want those shorting out against the heatsink either. Nice work. And there's our bridge rectifier down in there for channel 2, identical one on the other side for channel 1, but channel 3 is different. Let's take a look at that. So here's the circuitry for channel 3 wedged down in here, and you can also see that they've got relays down in here that are associated with channel 3. So that'd be like the channel 3 output switching relay and stuff like that. There's the filter cap, and there's the bridge rectifier. They've got just 4 standard diodes. They're like mounted like 10-15 millimeters off the board there to get some extra heat sinking on the leads. So you know, they don't require the same large power bridge rectifier that they used on the other channels, because this is only a 3 amp channel, not a 5 amp channel. So they've squeezed. There's a couple of current shunts down in there. You can see them. Oh, you can see them down here. Sorry, the light's pretty poor in here, but look at this. I mean, here's the main filter cap, and look how close it is to the heat sinks. It's only like, you know, 2-3 millimeters away at best, and that's going to get all the radiated heat, not only from the heatsink, but the worst of the heat sinks, this one here, which has to handle channels 2 and 3. So in theory, it's going to get the hottest, and so that's poor design. I mean, if you look at the other channels over here, there's a huge gap here. I mean, what's that, you know, 25 millimeter gap or something between the main filter cap and the heatsink. So that's not bad. So in terms of, you know, airflow, like it's not directly next to it, so the radiant heat is going to be less, but then the airflow comes through the unit, like the vent holes are up here somewhere, it all flows through, and these caps are going to keep reasonably cool. But the channel 3 one in there, don't like its chances. Sorry, I can't see the brand of that cap in there, but it's not, doesn't look to be the same as the ones on the main channel. And of course, everyone wants to know what the main caps are. What brand? Well, I'm glad to say they're a Nippon Chemicon brand, one of the top brands on the market. These are the KMH series, 105 degrees C, black. Ooh, black version. Oh, it's got to be better. And these are a 63 volt, 10,000 mic. And these KMH series are designed basically for this particular application, for linear power supplies, high ripple current, things like that. So these are rated for 2,000 hours continuous operation at 105 degrees C at full rated output ripple current. So not bad, assuming they're genuine. You can see though the silk screen on these. I don't know, can anyone tell me if they've got a genuine Nippon Chemicon? If you've got to watch this in HD. I saw this on one of my recovered footage videos. I can't see it on the screen very well here, but you can see that the silk screen almost looks not up to par, but hey, I'll give them the benefit of the doubt. They're genuine. You pay $450 for the supply. You want decent caps. Once again, look at all the residue left on the board here. Not impressed at all, but once again, the connector's glued down, which is good. And we've got some small heat-sinked regulators here. They're 7815 and I believe 7915, so positive and negative 15-volt rails there, presumably for the op-amps that are used on the DAC and ADC board in here, which we'll take a look at in a minute. So once again, they've got their own transformer tap here coming in, not a problem. They've got their own bridge rectifier, their own filtering, and there's an onboard regulator somewhere on this board down in there, which we'll see as well. And the output switching relays, what brand are they? Healy Shun. I don't know, may as well be one hung low. Wouldn't trust them, but I don't know, they might be reasonable. I've just never heard of them. Now, I'm not really a big fan of having the extra earth leads connected to the transformer lug over here because, well, they haven't scraped the paint off, and, you know, it's not the most reliable method. It's got to go through, you know, in practice it works, but it's not best practice, if you know what I'm talking about. So that's got one earth wire going off there to the front panel board. These don't go directly to the binding post terminals. As we'll see, the binding posts are actually connected to their own board in there. So that goes off to the ground terminal on the front panel, and the other one goes off to another lug on the main power supply board. And we've got ourselves a genuine FTDI FT232. No surprises there. That is on our serial/USB input board. And no surprises there, a Max 202 driver for the DirectRS 232 interface, and that board, you can see there, that board goes off to the D9 serial connector. So yeah, whether or not you use the D9 serial input or you use the USB interface, it makes no difference. It works exactly the same. It's just a serial interface to the machine. Not entirely sure why they have a relay on there. I'm not going to bother investigating, but yeah, don't know what that's doing. Now, one thing you won't notice on this board is any opto isolation at all, because, well, you might think, hey, that's a bad thing, right? It's not isolated. Well, you don't actually need it, because it goes off to the logic board, goes through this wiring all the way over to the logic board, and the logic board on the front panel has its own isolated transformer tap. So all of the digital logic interface here is mains ground referenced, because it's going to go back, because, well, it should be, because when you plug in a USB cable, it's also going to have the ground earth reference on it. So therefore, you have to run the logic circuit at that ground earth reference. Otherwise, you've got to use an opto-isolated interface, and you don't really need to do that. So no surprises that it's not there. And I'll show you that that's the case. Let's go between, no pun intended, hey, let's go between the case ground there and the USB input. There we go. That's the negative terminal of the USB input. So they're ground referenced, and you'll find that the logic board is also ground referenced. And you can see that there. We'll go between earth, and we'll go between the regulator tab there. There we go. It's the logic board on the front is mains earth reference, but nothing else is. Of course, the front panel terminals aren't. The actual voltage output terminals are completely isolated with their own taps and with their own logic, and we'll find the opto isolators are actually on the logic board. And there they are, as you can see, and that, folks, is a lot of opto isolators. They go all the way across the bottom of the logic board, because you need to have multiple serial interfaces to all three of the isolated channels. So that's why we've got three separate connectors there with the data going out. So there's a ton of isolation there. And of course, that logic board on the front panel has its own onboard regulation there. It's got its own transformer tap coming off. Yep, there it is, own transformer tap down there, and which powers all the logic. We'll take a look at the processor in there. And there it is. It's an STC Micro 89C58. And STC Micro are a Chinese company, non-mainstream. I believe it's an 8051 compatible processor. So yeah, not your usual, microchip or Atmel or, ST or any of the regular ones. This is STC. And other logic on the board, just lots of 74HC 74 down in there. Really, TTL stuff, nothing special. There's the crystal for the processor there. And sorry, I can't get these boards out. To get these boards out, I really have to take out the transformer and then essentially strip the entire power supply back to nothing, basically. And I don't want to do that. You can see that ribbon cable down in there going off to the display module on the other side. Nothing exciting. It's just a chip on board, off the shelf, graphic display module. Nothing happening there at all. So really no need to take that board out. And airflow wise, by the way, nothing special happening. They've got no airflow guards or anything like that inside. So air is sucked through the side vents at the front of the unit here. So it's goes over the transformer a little bit and then gets sucked through the heat sinks and out the fan, and the fan pushes out the back. And you can see tucked away right down in there is an M205 fuse, presumably for the output of the main transformer tap for each channel coming in there. So, you know, it's sort of a safeguard. I mean, you wouldn't normally expect that to blow because in, you know, general use, the current limiting of the channels is going to stop it. But it's good to know they've got some extra protection in there, and you can change it if it's a little hard to access. Got a couple of power resistors down in here, and they've got little heat shrink, little sleeves over the wires there just to stop them shorting out. Now you can't see it in this video because I've already straightened it up. It was in the previous video that got mangled by this pain in the ass camera. But these two current sense shunts, they were almost shorting. They were almost pressed together at this end down in here. So yeah, I wasn't very impressed with that. So I just nudged them back apart a bit. And I just confirmed that both of those power transistors in there for each channel are actually paralleled up. So they're, you know, they're using two devices as the main pass transistor rather than just one. And I'm not sure why, because one is perfectly capable of doing that. Maybe they just wanted the, you know, the extra dissipation and to get it into the heatsink a bit more efficiently than a single device. So of course this is a circuit topology where the one main pass transistor, or in two in parallel in this case, but they work just like one, is effectively doing both the voltage and the constant current limiting as well. So it's not like they're using a separate device for the current limiting. So with two devices, you know, there's multiple reasons why you might want to use two instead of one. I mean, these are like you know, 12 amp capable devices, more than capable on their own of the actual current handling capability, but you might want to spread your heat more efficiently across the two devices, and then the junction between the device and the heatsink is going to be a bit more efficient if you use two of them. It's just better that way. Spread your heat around a bit, and also hopefully they will run, well, they should run cooler as well, longer life effectively, and also possibly they just didn't have the gain required in one, so they spread it across two devices, so that could have implications in terms of the loop stability of the power supply and stuff like that. Maybe they found that one device just, you know, it wasn't stable enough, so we're going to spread it across two. But of course they haven't made that same decision with the channel 3 output, just the one device. Now let's take a look at this vertical riser board here, which is the DAC ADC board. I at first assumed in the first video it was just a DAC board, but I now find it's both. So check it out. We've got some TL071s, nothing precision happening there at all. And one thing you'll notice is look at the shoddy soldering on these. Look, the parts are at all odd angles. Look at them, and it looks like they've been hand soldered or something. Absolutely shocking soldering on this. Absolutely atrocious. Like, some are okay. Those SO8 packages aren't too bad, but you would swear some of those are done by hand. Absolutely ridiculous. And further down, another TL071 and a TL074 quad version. Woohoo! Look at the alignment of those resistors there. Dodgy brothers. And here's our DAC. There it is, little 8-pin SO package. And yeah, no surprises, it's a reasonable DAC. It's a Texas Instruments TLV5638, and it's a 12-bit voltage output DAC, single one. It's got a programmable internal reference. I think it's about 0.25% or something like that. Couldn't quite get the tempo of the whole thing, but it's in the order of like 10 ppm per degree C for the gain. Differential nonlinearity, less than half least significant bit. And it's monotonic over the whole range. So, you know, it's a reasonable DAC. Does the business. Serial interface, and of course, the absolute reference in here is not good enough at 0.25% to match the 0.05% absolute performance of this power supply. But as I've said many times before, it doesn't matter, because you can calibrate that out. This thing could be, you know, have a 5% reference. Makes no difference whatsoever. It's all about the stability and the drift with temperature. So as long as it's stable, Not a problem. Calibrate it out in software, and this software actually comes with calibration software, so you can tweak it, or at least you can get the calibration software. You enter the password and you can actually tweak the thing, and they obviously do that in the factory before they send them. But one of the biggest surprises I found on this board was this chip here, this little 14-pin package. It's actually an MSP 430 processor. It's an MSP 430F2013, and it's a mixed signal low power microcontroller. Not very powerful. It's only got 2K of flash memory, 128 bytes of RAM, but it's got a 16-bit Sigma Delta ADC with an internal reference, and you can bet your bottom dollar they're using that, because there are also alternative parts in this series, the 2012 and others that are, and the 2011 that are identical, but they don't have the 16-bit Sigma Delta ADC in them. So they're obviously using that. More than good enough for the purpose. Classic case of one of these little basic, simple, low-power mixed signal microcontrollers. Perfect application for it. Just controlling a DAC, doing the loop stuff. So, you know, you can bet your bottom dollar it's probably independently monitoring, the current on this channel, shut it down, the overvoltage protection, the overcurrent protection, stuff like that. Each individual channel has its own little 16-bit mixed signal processor. Not doing much, only 2K of RAM. They probably programmed it in assembly language, and it's probably talking to the DAC as well, controlling that. So good choice. I like it. And you can see some star grounding happening there. There's the star point. You can see them branching out like that. All individual points. Yeah, there's 4 running out the bottom there. They know what they're doing. Oh, and by the way, that Sigma Delta converter, 16-bit one, also has a programmable gain amplifier built in as well. Perfect little device for something like this. Not much else happening on the board, but we have a classic 1117 Jelly Bean. It's the, it is the standard low dropout voltage regulator. You see them in all the Teardowns. They're a dime a dozen, used everywhere, and it's got 3.3, so that's a 3.3 volt version, local regulation for the digital part of this. And it looks like we've got ourselves a little serial programming interface as well for the micro. Just look at the quality of that soldering, or lack thereof of quality. You got to be kidding me. That definitely looks like it's hand soldered, and look at the ugly residue left over. This board could do with a clean before it goes back in. Ugh. So, yeah, it's hard to tell what they've actually done here. Like, it looks like they have, possibly reflowed some things, but that's just, man, that just looks for all the world like it's hand soldered. And they've got one little optocoupler there, not entirely sure what that one's doing. Now, I don't know about you, but I can't help myself wondering what happens if I power it up without one of these DAC ADC control boards on one of the channels. Channel 2, I've got disconnected there. I followed the wiring. It is channel 2. Let's power it up. Now, if they design this thing properly, well, you'd expect, it would do some error checking. If it doesn't talk to it, it'd switch it down. It'd show an error message on the display. If they took pride in their firmware. Have they? Boot in. Come on. Let's go. You'd expect a power up error message. No, folks. Look, the fan has gone full ball. The fan normally doesn't go full ball like that, but channel 2 is still showing 24 and 5. Can we even adjust this? 24, let's say go. Let's go something stupid like 50. No, we can't enter that. Nah, it's not going to let us do that. 5. It allows us to set everything, but of course we're not going to get anything out. Whoa, I just switched the output on, folks. Check it out. 38.6, 6.6 amps. Are we actually getting that on the output? No, we're getting 0 volts. Nothing. So really, that's, poor design. I mean, you've got firmware in there. You've got, you're talking from one microcontroller and just doing the front panel to the other micro over here. You think you'd have some power on checks, and if there was a problem or something, you think it'd pop up with an error message on the screen. That's just poor form. Now we've got a third ADC DAC control board over here, and it's almost identical layout to the other ones. It's and the other one's longer, of course. It actually extends down there because it needs to attach to the top of the railing up there, but it looks to be an absolutely identical layout, except there's a whole bunch of transistors, or yeah, are they Q? Yes, they're Q, the designator there, so the transistors are not diodes, Q4 there. So they're all unpopulated, so I'm not sure what's going on there, but everything else looks identical, apart from two bodges. There is a bodge up there. You can see they've deliberately shorted 2 pins there. They've done that on purpose for some reason. And we have another little bodge near the processor. Don't know what that is. Ugh, that's terrible, Muriel. Now, while channel 1 and channel 2, the main channels, have basically everything on this main board here, including some current shunts on the other side of that board. I've plugged it back in so you can't see it. That's not the case for, well, channel 3 control board actually has some stuff down in the middle, as you saw before there. It has the pass transistor mounted on the heatsink, so half of it's there, and the other half is actually, well, here's the ADC processor board for it, but here is the secondary board, the main board containing lots of filter caps, and if you can see in there, a couple of current shunts as well. So that's all mounted on that main board, and then the wiring, see that blue and the red one, jumps over from the channel 3 board in there over to the binding post board on the front panel, and that front panel board has all of the binding posts connected to it and a couple of earth coupling caps and the odd relay, and that's it. And if you can see the binding post board down in here, you can see the earth cable coming in here, and then you can see the suppression caps. There's actually 4 of them. There's another one down in there. They would be fully rated caps, of course, but the markings are on the other side. Can't quite see them. You might be able to see some relays down in there on the front panel binding post board there for your parallel and series mode for switching your channel 1 and channel 2 terminals, either in series, parallel or independent. And you should just be able to see the binding posts down in there attached to the main board. Sorry, very difficult to see. It'd be impossible to take this thing apart. It'd take me hours and never get the bloody thing back together. But anyway, they do have, yes, they are shake-proof washers. You can see under the nuts on those binding posts, so they shouldn't give too much of a problem. Okay, what I'm going to do now is just measure the temperature of the heatsink and see what it gets up to. So I'm loading channel 2 and channel 3 here because they actually share the same heatsink, so that's worst case. So we'll only measure the one heatsink there. The other one's going to be identical performance minus channel 3. So I've got 24 volts at 5 amps, so that's 120 watts, and I've got 6 volts at 3 amps via a resistive dummy load here on channel 3, so that's another 18 watts, so like 138 watts total. So I'll leave it running for a little bit and we'll measure some temperatures. And of course I chose 24 volts there because that is the lowest, almost the lowest voltage of the highest transformer tap. So we should be getting, on the highest transformer tap, we'll be getting the most dissipation in our heatsink, the most voltage drop across our pass transistor, therefore the most dissipation in our heatsink. And we should, after we measure that temperature, then we'll drop it down to the next tap, which will be about 23 volts, and then there won't be much margin or voltage drop at all across the pass transistor, so the temperature should then start to drop. So let's feel that. Oh yeah, hurty, burny. Woo. So let's try and use our little IR thermometer here. You know, the emissivity may not be that great. It's showing that transistor, that diode bridge down in there, 8790, showing the heatsink or the edge of that getting up to 90, but I don't necessarily believe it. The 5 volt pass transistor there, 72. The laser is offset, by the way, when you're this close, 70 odd degrees. I don't particularly like that at all. I mean, you know, if you put it just on the heatsink, 37, it's hotter than that. So let's get a real temperature probe. Alright, let's try our Fluke CNX T3000. Pretty darn accurate device, designed for the purpose. We've got a K-type thermocouple probe. Let's get in there and let's get the temperature on the directly on the little stud for the screw for that 6 volt channel 3 pass transistor there. 62 degrees, 64. There we go. We're almost to 70 degrees on that 5 volt pass transistor, directly on the screw, of course. How about the diode bridge down here? That's about 77 degrees or thereabouts on the diode bridge. Let's do one of the pass transistors for channel 2. Yeah, we're getting up near 80, yeah, well over 80 degrees there on the screw. Let's see what our heatsink's doing. Now that's directly on the screw for the thermostat up there, so which is screwed directly into the top fin of the heatsink up there. So that's, you know, 61. I think I saw it get up to about 62 degrees. Heatsink, that's kind of what it felt like. Yeah, so I've had this going for maybe 10 minutes, and that heatsink is, you know, 65 degrees, something like that. I mean, sure, we've got the case off, but I wouldn't expect it to get too much warmer. I mean, that fan's going full pelt there, so really, you know, it'd be sucking a fair amount of air through, keeping it relatively cool. But yeah, as we said before, like I think those thermostat cutouts are, well, they've got 80 marked on them, so I presume that they're 80 degrees C cutout, and that would sort of make sense from a design point of view. Probably wouldn't want to get them much hotter than that, but there you go. We've got channel 2 and channel 3 on practically full load there, and well, we're 65 odd degrees. So what I'll do is I'll just change this down on channel 2. Let's go in here and VSET, and we'll just change that down until we hear the relay click. There we go, 23 volts. So we're now 1 tap down, but we're on the high side of that 1 tap. So we should be dissipating less power in the pass transistor. So our temperature should drop, in theory. So let's see if it does. Let's keep our probe. I'm going to put it back on there. Needs to get up to temp. I need to keep a consistent pressure on that, but we should actually see it eventually come down. It's just getting up to temperature, the thermocouple, but once it does, it should start to climb down. There we go, we might be seeing that now. And yeah, that's really starting to drop now. So before, what we saw with 65 degrees C was the worst case design scenario, worst case load scenario, really, pretty much. So although we could check all the taps and the various margins on all the taps, but geez, don't want to gild the lily, just want to get a ballpark. So yeah, that seems to be operating at quite a safe temperature, so pretty happy with that. Pretty well designed. They do know what they're doing with the multiple taps. I'm sure they've done their calculations and their thermal tests and measurements and all that sort of stuff, and for good measure they've put in the thermal cutout as well for any, you know, thermal failures with thermal runaway and things like that. So nice work. What's the brand of the stupid fan in this? Snow brand? 24 volts, 0.2 amps. What a pain in the ass. That thing's coming straight out. So there you go. I had to go through and shoot all that video again. Well, maybe I missed a few things from what I had in the previous one. It doesn't matter. It's like 7 o'clock on a Sunday night. I'm going to be in trouble, so I got to head home. Boy. So I hope you liked that teardown. That was the Atten PPS3205T-3S. And what can you say? Well, from a teardown point of view, it was basically what I was expecting. I was a bit disappointed with the quality of the soldering, but it's just a cleanliness and sloppiness in terms of assembly. So they've clearly shot this thing out to the cheapest assembly house in China. I mean, and it shows, but it seems to be quite well engineered. I'm impressed with, you know, Nippon Chemicon caps, and they've got thermal cutout, and it seems to be, you know, reasonably designed. Big, nice, beefy rated transformer in there. Nice, safe operating temperature seems to be. So, you know, I'm reasonably happy with it. I mean, you know, it's not a high-end unit. It's built down to a price, and well, the teardown kind of reflected that, because I didn't really find anything inherently wrong with it. You know, a bit of sloppiness here and there, but overall, not a bad design. So there you go. If you like the teardown, please give it a big thumbs up, and give me some sympathy as well for losing those bloody files. Pain in the ass, stupid dumbass camera. Oh, God. It's just like Canon's prosumer camera. You would, you know, top of the line prosumer camera. You'd think it'd be, you know, usable. Bloody hell. Losing files, inexcusable. Unbelievable. Anyway, if you want to discuss it, jump on over to the EEVblog forum. Catch you next time.